Get started again. So our second talk this morning is from Professor Lijing Shao from Kafle Institute for Astronomy and Astrophysics at Peking University, Beijing University. So Lijing is working on gravitational wave astronomy and pulsar astronomy, and also very interested in testing theories beyond general relativity and the standard model. So Lijing is going to tell us about testing gravity theory with pulsars today. Okay, please go ahead. You're welcome.
Thank you very much. It's my great honor to give a talk on testing gravity theory with pulsars. So we have heard a great talk using the pulsar timing array to test gravity and also to detect stochastic gravitational wave background. So here I will only talk about using the binary pulsar system to put some constraint on some aspect of modified gravity. So this is the outline of my talk. So first I will give some introduction to the field and then give some example to show the ability of pulsar timing to perform gravity test. Yeah. So as we know, the modern physics is composed of two parts. One is the standard model, which is described by the quantum field theory. The other is general relativity, which describes gravitation as the dynamics of space-time. But these theories, they are very successful in explaining a lot of observational effects. But however, they are not compatible with each other, at a current formulation. If they are not compatible, if they are not consistent, we know one of them must be wrong, or even maybe both of them are wrong. This will be the ultimate feat of these two theories. So there may be some effective field theory or some approximation of a more fundamental theory. So we want to have some way to new physics, the possibilities. So as we know, there are two major problems in astronomy and cosmology. One is the dark matter and the dark energy. Both of them are dark, which means we don't know about the nature of them. There are also need a new field for the inflation, and also there are some evidence for heavy double boson, and also there are firm evidence for neutrino mass. They all go beyond the minimal standard model and the minimal general relativity. So give a very short summary. Up to now, the theoretical physics is very beautiful, but not yet complete. And in describing the four fundamental forces in the nature, three of them are described by the quantum field theory. But one of them, the gravity, is described by general relativity. So in this sense, maybe gravity is holding the key to next level of the new physics. This is just one possibility. It's a plausible one. Okay, so I will give some introduction about using binary pulsar timing. So first I will talk about what is pulsar timing and what is the principle behind the pulsar timing. So pulsars, they are basically rotating magnetized neutron stars. Their momentum of inertia is quite large because they are a macroscopic object with the mass of the solar mass and the radius of 10 kilometers. The momentum of inertia is large. And they are in the space, and the external usually is very small. So in this case, we know by conservation of angular momentum, the rotation of the pulsar is very stable. So when you have something which has stable periodic motion, so here is the rotation of the pulsar. We know by physics we have a clock. We have a very good clock from pulsars, for the rotation of the pulsars. So this is actually in ancient time, people using the rotation of the Earth and the rotation of the Earth around the sun of these things to define the flow of time. So this is another way to have this kind of clock. So pulsars are not only clocks, they are also precision clocks. So this is, I give one example for one particular pulsar. This is a measurement of the spin frequency of this pulsar. So usually in astronomy, we do order of magnitude estimation, but in pulsar astronomy, we don't. So this is the measurement of the spin frequency, and this is the last 2 digits. Here is the uncertainty of this measurement. This measurement is very precise. If you count the digits, you can already see it's 16 digits. 16 digits means it's reaching the limit of floating numbers in the computer system. So we need, even if we want to go beyond this digit, we even need to have take care of the floating number precision in computer science. Okay, so this is a sense of the clocks, or what kind of clock we have. So actually, we just mainly divide the pulsars into 2 groups. This is the pulse period and the time derivative of the pulse period of pulsars. If we plot them, you can visually see they are basically 2 groups. And in this group is the so-called millisecond pulsars. And I also put the binary pulsars in circles. This red circle means this pulsar is in a binary system. So by some evolution reason, the binary pulsar, the millisecond pulsar are mostly in binary systems. So these kind of millisecond pulsar, we can do very good timing of them, and they are the main object of this talk. And actually, there is also a triple pulsar, only one triple pulsar in this blue square. Okay, so pulsar timing, basically we have a large radio telescope on Earth, and use this telescope to receive pulses from the pulsar. So we only do one thing, which makes this experiment very powerful. So we only record the times of arrival of these pulses. Just to record these numbers, when you receive a pulse, you record the time of arrival. It's very simple. Because it's so simple, it's so powerful. There are not many systematics in this experiment. So these times of arrival are affected by some factors. The motion of the telescope around the sun, which is actually very well known from satellite observations. The other is the propagation of these pulses in the interstellar medium, which is controlled by the plasma physics. You have a frequency-dependent delay, and this actually is also very well known. And the other thing is, if a pulsar is in a binary system, it's in the orbit with its companion, and this motion will also affect the times of arrival. And this motion is mostly controlled by the gravity of the pulsar and this companion. If the gravity theory is different, then you will have a different motion, and this motion will be reflected in times of arrival of the from the radio telescope. So this is the basic idea behind the pulsar timing. It's very simple, and it's very powerful, and it's very precise. Okay, so this is just one example, shows what kind of telescope we use to observe pulsar. This is a 500-meter telescope in China. It's the largest one on the Earth to observe pulsars. Pulsar is one of the key signs of this telescope. So for the neutron star, pulsars are neutron stars. For neutron star, we have some some super properties of neutron star, which is summarized by Davis Panis, who is not an astronomer, but he is very fantastic by the neutron stars. So we call it Panis theorem. So the theorem says neutron stars are superstars. Because they have some super property. They are super dense. The density is larger than the nuclear density. Also, they have super strong gravity. They are almost a black hole. They are also super fast spinning, and they have super precise timer. And they also have some other properties, like the super glitching and super conducting property, and with some super fluid, and also have super strong magnetic fields. And also they are super rich in physics. So there are only 2 objects we know which involve the 4 fundamental forces. So they all play significant roles. One is the neutron star. Neutron stars, the strong force, the weak force, the electromagnetic force, and the gravity. They all play significant roles. The other object, these 4 fundamental forces play significant role is the early universe. These are only two objects we know which involve all the four fundamental forces. They are also born in supernova. So they are super stars, neutron stars, superstar. So because they have so many super properties, they are truly extreme laboratory for fundamental physics, including strong gravity and also including testing the non-perturbative QCD and also some unique strong physics and so on. So in this talk, I will focus on the strong gravity. Okay, so for binary pulsar, in Newtonian gravity, we know they are in some eclipse, and but in the general relativity, they have extra effect, extra dynamics, like the precession of the perestrian, and also the orbit get smaller and smaller because of the radiation of gravitational waves. If the pulsar is behind the companion, the pulse is when it comes to our telescope, it also goes through the curved space-time of the companion, which introduces some delay, the so-called Shapiro delay. These effects they can all be measured by the radio telescope, by the Pulsar timing technology. Okay, let's see the precision of this measurement. So just focus on one example. So here we show the one example on the shrinkage of the orbit because of the radiation of gravitational waves. The shrinkage is like 7 millimeters per day. It's very small, millimeters per day, and the precision is a micrometer per day. This is just one example. Just one example. So which tells you how precise the Pulsar timing can be to measure this relativistic effect. Okay. In the Pulsar timing, we usually fit this the phenomenological parameters which are listed here, like for example the PB dot. PB dot is the time derivative of the orbital period, and also the omega dot is the time derivative of the perestrian angle. And these parameters, they are directly extracted from the timing data. And in a gravity theory, these parameters are related to the dynamics of this orbiter. And usually, it's here I give the expression. They are very lengthy, but they are well calculated. These are the expressions in general relativity. And if you have a different gravity theory, you have different expressions for these parameters. And here, although they are lengthy, there are only two unknowns in these expressions. It's the mass A and the mass B. They are the two masses. The other parameters, this PB and this eccentricity and so on, they are very well measured because they are basically the capillary parameters. So there are two unknowns. And if we measure these parameters, for one parameter, we plot a curve in this plot, in this mass diagram, because there are only two parameters control this measurement. And if we measure 3 parameters, we can ask if the gravity theory is consistent or not. If the underlying gravity theory is consistent, these 3 lines must meet in one common region within the measurement uncertainty. Okay, this happened to the first Husserl pulsar, and this shows the evidence for the existence of gravitational wave, and Husserl, they got the Nobel Prize for this measurement. Okay, so now the current state of art is not the Husserl pulsar, it's the binary pulsar. For binary pulsar, we have observed both objects as pulsars. We can record all this pulse from this neutron star and pulse from this neutron star. For this system, people have verified the Einstein's gravity, the quadruple radiation, to a very high precision. So here I show the prediction from Newtonian gravity, which is basically the perestrian time shift, is 0 because it's on a very stable. The orbit is not changed for every orbit. The Newtonian gravity, the orbit is stable. But in general, the orbit is shrinking, and you get this prediction, which is the green line. The green line. And this white dots, they are measurement. This, I would like to emphasize, this green line is not a fit to the data. It's a prediction of the data. It's not a fit. So this you know the consistency is astonishing. Is astonishing. This is the best measurement of the quadruple radiation up to now. The precision is better than 0.01%. Okay, in this system, if you plot it in the mass diagram, because we have two pulsars and we have many measurements, actually we have seven measurement of parameters. If the gravity theory is consistent, and then all these seven parameters should meet at one single point. And this you can see by zooming in here, and indeed they meet at one point. This is the best measurement of the best test of the generativity. So this is very hard to alternative theory to pass this test simultaneously. Okay, so I hope I have convinced you that pulsar timing are very sensitive to small changes in orbit. Thus, they are very good laboratory for gravity theories. Okay, let me also show you another aspect, which is called the strong field gravity. So, pulsars, as I said, pulsars are precision clocks. They are not only precision clocks, they are also precision clock in highly curved space-time. Because pulsars, as I said, they are almost black hole. They are almost black hole. So in this case, we can measure the strong field effect. So by the strong field effect, I mean this part of parameter space. This is the parameter space for the gravity test. The horizontal axis is v over c, the typical velocity, and this vertical axis is the typical space-time curvature. There are many experiments, you know, the cosmology and also solar system satellite experiment, and also the pulsars and gravitational waves, and also black hole image, so on. And here, this region is the region we call the strong field gravity region. So, which means the velocity is close to the speed of light, and also this space-time curvature is large. So this region is important for gravity theory, because gravity theory is very well constrained in this solar system experiment, which is the weak field region. Okay, let me show you one example. One of the alternative gravity theory is so-called the scalar tensor gravity. It's a very old one, but it's the idea of field gravity. So in this action, we have this Einstein-Hilbert Ricci scalar here, and then we just add this the kinematics of the scalar field, and also some potential. But in my setting, I will just choose this potential to be 0, just to be simple. Okay. But there is another thing here. This conformal coupling of the magic to coupled with the scalar field to the matter. So the matter feels this metric, which is rescaled by this phi. This A is a function of phi, by rescaled by this scalar field. I will just choose this simple form. This must be positive, so I just choose this exponential, but here introduce a beta naught parameter. Okay, so at the infinity, there will also be the cosmological background of this phi field, which I denote as phi naught. So we define we define a theory by just the two extra parameters with respect to the generativity, which is phi naught and beta naught. Okay, this is the so-called scalar tensor gravity. Actually, it's sometimes we call it the Esposito-Fraser gravity. In this gravity theory, you can work out the field equation and then work out the modified TOV equation, and then you can integrate the TOV equation using some equation of state of neutron star. You will get something like this. So let me explain. This is the fractional gravitational energy, which is the gravitational energy divided by the rest mass. This it's a dimensionless number. And this is the scalar charge. You can view it as the deviation from generativity. Okay, so when this fractional gravitational energy is small, this deviation is very small. It's very small. But at some point, this deviation is activated, and it becomes very large. Please notice this is a log scale. If you really plot it in a linear scale, it's just a peak, just a peak. Okay, this is the so-called non-perturbative spontaneous scalarization, because the neutron star will get scalarized in this theory and can deviate as large as order 1 from generativity when, in the meantime, they satisfy all the weak field limit, all the weak field experiment. So this is one example where we can imagine that the gravity is still generativity in our solar system, but in the strong field, it has a very large deviation. Okay, this can actually be understood from various aspects. We can understand from this Landau's phase transition. It's kind of a gravitational phase transition behavior. Okay, so just a very short summary that gravity in the strong field can be very different from weak field. This is at least I should one explicit example for this. Okay, so we can test this in the strong field. To test this, we usually use yeah, please.
I'm guessing. This is happening for neutron stars of a given like 10 kilometer size or so. But if I had, I don't know, a different type of matter, neutron stars of, I don't know, like 10,000 kilometer in size, would the same thing happen? I'm just saying, is it the size or is it the strength of the gravity that?
So here, this is a very good question. So here, actually, it depends on the theory parameter. For some theoretical parameter space, this phenomena do not happen. But for some part, but we don't need to fine-tune them. But for some part of parameter space, this happens. And this is just one example. It's called scalar tensor theory. There are also other examples. They also have similar behavior, like if you have some corresponding term and so on. They also will have this behavior. It's not happen for all alternative theory, but it's not fine-tuned. Okay, give a question. Yeah, yeah.
So you're saying that 7 curves join up together already show how wonderful GR already can do. So
Yes.
why like people want to come up with this kind of other like scalar tensor gravity behave like this? So what's the motivation here? Is that from the neutron star? No.
Yeah. I will talk about this in this slide. Okay. So if we want to test such a theory, if we need to predict the observables from this theory, they can be scalarized. But what are observables? So in this case, the most significant observable is the dipole radiation. If a neutron star is scalarized, the system is likely to have dipole radiation. But if these two stars, they are both neutron stars, if they are very similar to each other, they are both scalarized. In that case, the dipole radiation will be very weak. So this is the case for the double for the double pulsar. They are both neutron stars. Even in this theory, the dipole radiation will be weak. Okay, but if these two objects they are different, one is, for example, one is a neutron star scalarized. One is a wide-off weak field object. It's not scalarized. Then in this case, you will have larger dipole radiation, which is proportional to the difference of two scalar fields as a square. Okay, so this is why in this theory, the best system is not a double pulsar. It's a neutron star wide-off binaries. So this I just show two examples for this for the neutron star wide-off binary, but the agreement is still here. It's still here, which means this is these curves are predicted from generativity. They still meet at one common region, and this we don't observe this dipole radiation. And we can put a constraint on this dipole radiation, and then can convert the constraint into the theory parameter, constraint on theory parameters. Okay. But there is one tricky part is that we don't really very much understand the equation of state. So actually, there are degeneracy because we have to integrate the TOV equation in order to get the neutron star structure. And the equation of state and the gravity theory, they have some, they are degenerate. So, but luckily we have multiple systems, and even there are uncertainty in neutron star in equation of state, because we have multiple systems. This binary pulsar, this neutron star, they have different masses, and even they are degenerate. We can use multiple systems to kill this degeneracy to some degree. Okay, so this was first proposed by Shibata, and then we had some paper to explicitly show this degeneracy is broken to some degree of freedom. Okay, so this is the current best constraint on the scalar charge. So these different curves, this different color, they show different color are for different equation of state. So because we have this measurement, so we can see if we consider all these measurement, no matter what is the equation of state, the scalar coupling is smaller than 10 to minus 3, using all these current best data. So basically, we have closed this scalarization window for this simple theory. But of course, there are some variants of this theory which can escape this constraint. But for this simple theory, we have put constraint to the level of 10 to minus 3. Okay. But in the future, the gravitational wave observatories, this Cosmic Explorer and Einstein telescope, they will put a better constraint than the binary pulsar systems. Okay. Okay, this is one example shows the strong field gravity. And also I want to say that pulsar timing are also useful in other aspects of gravity theory. I will just show example of the massive gravity. So they are not a typical dipole radiation test, but they also have some extra channels in emitting gravitational waves. So this gravitational wave will carry away extra energy, and this makes this shrinkage of the orbiter faster. This can be detected by pulsar timing. So this is one example. This is called the linearized field Pauli theory. This black part is just generativity, the linearized generativity. And there's some way to add a mass term here. Actually, it's a unique way if you ask for these two conditions. The condition is if you want to have a standard form for the wave equation, and if you want it to recover generativity when this mass goes to 0. This term is the expression of this term is fixed. Okay. In this theory, if you work out the gravitational wave radiation, you can find some extra radiation which is proportional to the mass square of the graviton. Okay. Then we can collect all the pulsar systems and using some Bayesian analysis and to put a constraint on this extra radiation channel. This actually we get a constraint on the mass of the graviton in this linearized field Pauli theory. Okay, this is the best constraint in this theory. Okay, but this is theory dependent. It's not a theory independent, it's theory dependent. Okay. If you have other kind of theory, like this is the cubic Galilei theory, which actually has some screening mechanism, it can explain the dark energy behavior and so on. But this can also, dark energy is a larger scale behavior of the gravity. But this can also be constrained in this local system, like the binary pulsars. Okay. For this theory to be true, there is some, this pi s is a scalar field introduced in this theory, and it has some screening mechanism, but screening is for the fifth force. It's less screened for gravitational radiation. This was calculated by Deham et al. But they found some extra radiation channels are still introduced. There are multiple, actually. One is there will be extra monopole radiation, and there will be dipole radiation, and also will be extra quadrupole radiation. all these radiation should be combined and should all contribute to the evolution of the binary, and they can be detected by pulsar timing. Okay. There are some investigation on which kind of system are the best to put a constraint, this eccentricity system, and also some orbital period. This radiation are dependent on the eccentricity and the orbital period. Okay. So we have collected all the best pulsars to put a constraint on this theory, and this is a constraint from 14, I guess. I think it's 14, the 14 best timed binary pulsar system. And these constraints are very tight, actually. This is all the constraint, and this is the combined constraint from all these systems. The best part is contributed by this whole-stellar pulsar, and also this double pulsar. This is some constraint here. And the best constraint we have is 10 to minus 28 EV, which is actually much tighter than the kinematic test from the LIGO-LIGO-Kagura collaboration, via the modified dispersion relation for gravitational wave and so on. But I would like to mention again, this limit is theory dependent. It's not generic, it's theory dependent. Okay, but this shows actually an interesting example that some local system can test a theory which is designed by the larger scale structure for the cosmology. The data are from 14 pulsars, but the best one is this pulsar and this pulsar. These pulsars are timed for a long time. This pulsar is timed for a long time. It is the first binary pulsar, and this pulsar is just to show this double pulsar. Has very good precision for this pulsar. Yes. Yes. Right. Exactly. So this gives the best constraint in this theory. This constraint can even be improved if we can observe a pulsar around a black hole. This can be, can be some black hole, stellar mass black hole, or in some cases, it can also be the supermassive black hole at the galaxy center. So these systems will even improve this test. The current test is this blue line, and can be improved by maybe 2 orders of magnitude. Yes. Yes. Lambda is the length scale, the energy scale, which has I don't know exactly. It's like m squared times mg equal to lambda to the cubic kind of this. It's a one-to-one correspondence. Yeah. Okay, and in order to measure, to get this system, we haven't observed yet. We haven't discovered pulsar black hole system yet. But this is one of the key science program for the square kilometer array, which is under construction right now. It will start observing in 2027, which is 3 years, from now. It's still already under construction. Okay. This theory I would like very briefly mention. They are also useful to test the Yukawa gravity, which can put a constraint here. This is a parameter space not probed by other experiment. This is the Yukawa the extra Yukawa coupling here, and this is actually almost 4 orders of magnitude better than the S stars. The S stars are the optical infrared observation of the main central star around the supermassive black hole. And if we can observe supermassive black hole, pulsars around supermassive black hole, we can improve this test, this Yukawa gravity, by 4 orders of magnitude. Okay. So finally, this is my final topic. So pulsars are not only useful to test the gravity theory, I also want to mention one aspect that the pulsars are also useful to test fundamental properties of matters. So here is I will focus on one aspect, which is the fifth force from dark matter. Okay, this uses the conservative dynamics. They are not only, previously I was talking about the gravitational wave radiation, which introduced the decay of the orbiter. They are the radiative aspect. So here I want to talk about the conservative aspect of the orbiter. This is related actually to Queen's principle. Queen's principle is one of the fundamental principle behind the general relativity, and it says that gravity is accelerated system. It basically is equivalent to each other, and which also forms the fundamental aspect that gravity is just a curved space-time. This is a very, very deep principle behind the gravity theories. Okay, this actually was tested to very high precision by different measurements, starting from Newton and Galileo, and now the precision is 10 to minus 15. But these tests actually are only tests of weak Equus principle. By weak, I see the classical example of Galileo dropping two balls towards the bottom of the tower, and these two balls, they reach the ground at the same time. But these two balls, they are not a gravitating system. These balls, they are bounded by the electromagnetic force, strong force, and so on, but not by the gravity force. But the gravity force, they introduce the negative, gravitational bonding energy. If this is significant, this also contributes to the mass via the E equal to mc square of this Feynman's formalism. But this introduces, how the gravitational energy responds to the gravitational field. This question, which is the strong field, strong principle. If the gravitational energy responds in the same way as the electromagnetic energy to the gravitational field, then we see the strong principle is conserved. Okay, so this actually is characterized by this number. This number is very small for our familiar objects, like even for the sun, it's a 1 millionth, one part in a million. But for neutron stars, this can be very large, can be 0.2. And for the black hole, it can even be a little bit larger by maybe a factor of 2. Okay, so currently, GR is the only valid theory that preserves the strong principle. This is actually, if you test the strong principle, you are testing GR itself. Okay, so this is why the strong principle is very, very important here. So let's think of an experiment that we have a binary system and in a galaxy. And this binary actually, in the viewpoint of GR, they are doing the free fall in the galaxy potential of the Milky Way. Okay, if they should have the same acceleration if the strong principle is preserved. Otherwise, if they will have some difference in the acceleration. And if the strong principle is violated, this difference in the acceleration will introduce some characteristic changes in the orbital dynamics. So this is worked out by Damore and Schaeffer in 1991, which shows the eccentricity vector of the binary will evolve in a characteristic way. This is to show it illustratively. The eccentricity vector is composed of two parts. This red part is introduced by strong principle, and this blue part is just the vector. The eccentricity vector in the general relativity is rotating at a constant rate. It's what we know as the periostron advance. Okay, so this will introduce a characteristic signal in the pulsar timing and can be constrained via pulsar timing. Okay, this is the pulsar timing testing the strong principle. This also gets some limit, which is not as tight as the weak principle, but still there gets some limit here. Okay, this is the limiter from a binary pulsar. This is also a limiter from the triple pulsar. Okay, I will skip the triple pulsar system. And the best limit is currently 1 millionth from the triple pulsar. Triple pulsar is like you have an inner binary, which is in let me just show you, in an orbit of almost 1 year. So the inner binary is in orbit is 1.6 day, and this binary is orbiting a far away wide off. It's this triple system is in a plane and in this such kind of configuration, and you can view it from the point of view of generativity. That this inner binary, the two objects, they are doing the free fall in the gravity field of the third body. Okay, this can put a constraint to this to the level of this level. This is some recent result, and this tests the universality of free fall for strongly self-gravitating object. Okay, and we think that for the binary system, not for the triple pulsar, but for the binary system is the galaxy potential. This galactic potential, actually the gravitational potential, is produced not only by ordinary matters, but also by dark matters. We know half of our galaxy is dark matter. So this, if the dark matter has some other interaction with ordinary matter besides the gravitational interaction, then this will also introduce some changes to this strong principle test. It will introduce some apparent strong principle violation signal to the binary, and this can actually we call this the fifth force. This is the long-range interaction between dark matter particle and the ordinary particle, and this introduces some signal which is very similar to the strong principle violation signal. Okay, this is benefited from also from the material difference for the binary, which usually is the neutron star wide-off system, and also benefit from larger gravitational bonding energy of the neutron star. Okay, let me skip all the details and see that the binary pulsar they put the best constraint to this kind of long-range fifth force from dark matter. And the triple pulsar, they don't, because the gravitational field is produced by the ordinary, ordinary matter wide off. Okay, it's not from the dark matter, so it does not matter. It does not matter in this test. Okay. So currently, the best limit is from this pulsar is J1713 pulsar, and the conclusion is the following. If there is a long-range fifth force between dark matter and ordinary matter, its strength must be smaller than 1% of the gravitational energy, of the gravitational force. Otherwise, it will be inconsistent with the timing data from this pulsar. Okay, this is the best test from for this non-gravitational long-range force between dark matter and ordinary matter. There are also some other tests from different experiments, but this test is the best test in this sense, and it put a very tight constraint on the fifth force. And this fifth force this test can be enhanced if we can observe a binary pulsar close to the galaxy center. Like within 10 pc of the galaxy center, because there are predicted to be some dark matter spike there, and the density of dark matter is higher, and this will be stronger. And if we can observe this kind of system, the test can be improved. Okay, this is the test of the long-range fifth force between dark matter and ordinary matter. It's very complementary to the dark matter experiment that we have on Earth, like the underground detection of dark matter. They are searching for they are searching for short range force between the scattering of dark matter and the nuclear proton and neutron. Okay, this is another aspect, testing another aspect of dark matter. Okay, so this is basically come to my summary. So I hope I have convinced you that radio pulsars, they are precision clock. They are sensitive to tiny deviations from GR in the orbital dynamics. And they are extremely useful to testing fundamental physics. I have talked about some aspect, but not all. But the space-time symmetry they can also test. I didn't cover in this talk. They can test the strong field and massive gravity and so on. They are because they are so precise. They are so sensitive to the change in the dynamics. So they are useful in testing these fundamental properties. And up to now, all the tests shows Einstein is still right. But who knows? We may detect some beyond GR effect, sometime soon, maybe. That's the end of my talk. Thank you very much.
Hello, Professor. I'm a senior high, so Chinese.
Okay, Chinese. Okay. Sorry.
就是您提到，因为美国的 LIGO 它测了短波长高频的那一段，所以我们的 FAST 要去测低频长波长的那一段。然后因为广义相对论在这个理论基础上表现的比较好，所以利用广义相对论，您提出要用脉冲星去测量。但是您还说脉冲星是非常有力的时钟，但是在我的印象里，好像有一些个。就是 Young Pulsar 它有一些突发状况，可能会导致一些问题。然后您利用了一个大的，就是就是一个好像是阵列，脉冲星的阵列去测量。那么就是如果出现这种问题的话，可能会导致data error。那在 process 它的就是在处理数据的时候，这可能有什么讲究吗
？So I will repeat. 我把问题翻译一下给他听啊。I will translate the question. So he is asking, these pulsars, they may have some glitches, and they may, introduce some noise. Okay, so the answer is this pulsar. Usually we use this pulsar to test the gravity theory. OK， 用中文跟你解释，就是这些年轻的脉冲星，它会有些 timing 上的问题，就像你提出来的，会有些比较大的噪声出来。但是我们主要是用这边的比较年老的这个毫秒脉冲星去做这个检验，所以这边并不存在这个，就是我们不用这些脉冲星去做检验，我们用这些比较年老的，因为它的测试精度其实更好，用它去做检验。
这样子。
Thank you. So it's a very, very interesting talk. Covered a lot of ground. I think one question that at least I remember I had is the last part of your talk. I don't quite understand what this dark matter force, how that affects pulsar timing.
Yeah, actually, I have skipped some detail, but I'm very happy to explain these details. So we are assuming a fifth force between dark matter and ordinary matter. This which means the dark matter is coupling with ordinary matter somehow. Somehow they depend on a mixing angle. How the dark matter. Let me just show the slide. Moment. Yeah. So this is a mixing angle per side. This is how the dark matter couple to the proton versus the neutron. So we have like sin psi proton, sin cosine psi proton. This kind of force. This force apparently violate the coupling to the proton and the neutron. It's different. Which is kind of apparent strong principle violation signal. So let me say this in this way. If we assume, if there is such a first force, but we still assume there is only 4 fundamental forces. We ascribe this force to the gravity. If we do this, then we will see a signal which is the coupling is different for the proton and the neutron because of this coupling.
So is dark matter, what kind of a coupling does it have to protons and neutrons? I guess that's what I'm trying. You say it's a kinetic mixing, or what is the coupling of the dark matter?
Yeah, this is actually generic. It's not it's not related to the detail of this coupling. If this is actually some popular parameterization in this field, and people parameterize this psi using psi to have a force coupled differently to the proton and the neutron. But this also have some background theory, some fundamental theory which can give this psi. Okay, so, but I'm doing it in a generic way. If this is generic and this coupling exists, and you ascribe this interaction to gravity, then you will see some apparent violation of the equivalence principle.
So is it then that, so the pulsar, is it because the two different pulsars have different, this is the pulsar and the star have different then compositions?
Yes,
okay.
Exactly. So we are considering using this system. This system, we know it's a neutron star White-Dwarf system.
Okay, I see,
And the
I
neutron
see.
star, basically all of them are neutrons.
I see, I
The White-Dwarf half neutron, half
Very
proton.
good, I understand.
Yeah.
Okay, very good, thank you.
Thank you.
Do you have more questions? Okay. Thank you, Lijing.
Thank you very much.
So if we do not have more questions, let's thank Lijing for a very nice, interesting talk again. Thank you.